Alright, so, it's been a while since I last streamed. I started training. Fairly disappointing results. Yeah. I wrote some notes. Let's just pull those open for future work and just kind of the state of affairs and stuff. Wait, let me just shake this around, make sure I'm recording. Alright, so, yeah, edited May 30th, so then just like 2 or 3 days ago. Yeah, just this bot training brainstorm. Training is super slow. A single game at 400 MCTS simulations takes around 40 minutes and has 1400 moves. The bot seems okay. First of all, like stuff has been changed since then, since I tried a new net architecture. But anyways, bot seems indistinguishable from random moves. No progress. Tweak game mechanic. Okay, so yes, this is the main issue. The main issue is the first bullet point, that it's really slow to actually train the to run self-play. Sorry. When I say training is super slow, the actual like training when you're doing model.fit, like when you're training the net, like like using stochastic gradient descent. Like we're not using Atom, we're using we're using SGD, but anyways, that's really fast. But like the main bottleneck in this Alpha Zero implementation is self-play, like the actual games, like the inference, like model.predict. Each, like if you're doing like MCTS, like we have 400 simulations, well technically 401 for the root node. Like each simulation, 40 minutes, 1400 moves. I remember like figuring out somewhere or doing some computation that like 200 simulations, 200 predictions or so, like simulations is like takes about 1 second. We could do the math here, but anyways, like basically have to multiply the number of moves by the number of simulations per move, and then we can compare that against time to work out how many simulations per second or whatever time unit we choose. So yeah, the main issue with training this, which I haven't really made that much progress at all, is that training is very slow. Like let's pull up this this thing right here. I have two terminal tabs open. Like if you look here, like yeah, like this is the one that's open, like PS. We have 3 node servers running, like we're running the bot right now. If I do a CP, like kind of like we're copying the latest edition of the model, right? And then do a get status. This shows that like we already have the latest bots. So the latest model weights. So like we're not seeing like we're only seeing stage files. We're not seeing like unstaged differences. Like get diff will give us nothing, but get diff staged would give us something. Anyway, so back to what I'm saying. Like I'm lamenting the fact that training is very slow. So like here are some training runs, right? Yeah, I had to make number of iterations 1. So basically like first of all, I changed that to 1. So basically what's happening, like first of all I compiled train.ts, right? And then I keep repeating this command, train caffeinate no train.js. And I keep repeating that a whole bunch of times, right? And then once we finish the last one, then I just kind of added everything and then like kind of CP'd it over to BumperCoins to use the latest network. But anyways, let's just kind of go back to this. So what's actually happening, right, when I run this command? So first of all, we're running 1 iteration, and how many games? I'll just state it. Like we're running, like whenever I run this command, we're only running 1 game of self-play, just a single game, right? A single game, and like we can see how many like number of examples per game, and then we're training off of those examples. And the game has like this many moves, like some number of moves, and each move we're doing some number of Monte Carlo simulations, and that number is currently set to 150, I believe. So 150, 151 if you consider the root, I think. So like 150 simulations and 1 game. In fact, yeah, let's just like look that up. Less train.ts. Yeah, like 1 iteration, each iteration only 1 game. Like that's it. 1 times 1 is 1. Like 1 game per command of train. And if you look at mcts.ts, then the number of simulations is currently at 150. So those are the constants that I've trained this bot under, the latest edition. And each time like 1.5k, this is like pure random almost, and 1.7k, 1.1k, 1.2k, 1.1k. Okay, no, stop. So the first time we run it, it takes like 1700, let's just say around 2000 milliseconds, then around 3000 milliseconds, 1.5. Wait, no, this is the training. Sorry. The time commands output is right here. 1 point, yeah, one like about 1k seconds, and then it takes like 800 seconds. Then it takes like 800 seconds. I'll just keep scrolling down. Yeah, so you can see the examples start to like increase, and like basically like the examples, if you look at the number of examples and how long it takes, like this ratio should generally stay the same. Like if you do like 1.1 divided by 0.8 or whatever, like 1111 divided by 866, that ratio should typically be the same for all the runs, because the number of examples is like the bottleneck, right? Like if you take this and like kind of double it to like, let's say this one, like from 1.1 we get like, or 2.5, right? Then the amount of time that takes is like 2k seconds. So like from 1.2 to 2k. So like the ratio basically kind of, yeah, that's the ratio we're working with. So basically, so first of all, okay, let's just scroll down. So as you can see, like first of all, it's like kind of 1.5k. It's like in the teens, I guess. 18, 11, 12, 11, and then suddenly it's like 25. It's like from 1k we're in the 2k. Goes back down to 18, then 2k, then it's going to 3k. Like 3k, 2.5k, and then suddenly it goes down a bit, and then it jumps to 4k, and then like it's overall getting higher, I guess. Like 2k then kind of drops down, 3k, and almost, or yeah. So that's it. And like, well, we can look at the loss functions too. Let's like look at overall loss. Like 9.01, 8.2, good. The loss is going down. 7.89, 6, almost 6, 5.5, 3, 2, almost 2, 1.5, 1.7. So here's where it finally like kind of everything was decreasing until here. Now it increased, then it decreased, increased. So like we're kind of like bouncing back and forth here. Then it decreased, really, then it decreased. We finally broken the 1. Then we're kind of going up, seems to get worse, goes back down. So we're kind of like floundering here about, okay, good, nice. Kind of goes up, and then kind of goes up again. And then here's where I kind of like stopped, and I kind of like gave I CP'd into BumperCoins the latest weights. So a lot has happened, basically. Let's just do a git log. Okay, so, here, I believe, is when we ended last stream, and then I tried, ignore the emotive, yeah, forget it. Point is, I tried a different net architecture, because one thing I noticed when doing training after ended stream was a loss function wasn't even changing. Like, you see how it's kind of like going down from like, sorry, Q, or you see how it's kind of like going down like a bunch from like 9, from like, like 9, 8, 7, all the way down to like where we're currently, I'm not going to say stuck, but we're oscillating at. So like I noticed that it wasn't really changing, so I did a different net architecture. Basically the only difference was I added more convolutional filters, and I added some batch normalization layers, and that's it. As for why I did that, I mean, I guess Stack Overflow. Like I noticed the loss didn't change, and I saw like that some people mentioned that for ReLUs, like you know how like it's kind of like a flat line goes up, like the gradient, if it's negative, like let's say our bias term is like super negative or whatever, then like if the inputs to that perceptron, that neuron is like negative, then the activation function of ReLU would kind of make that 0. So the gradient there will be a 0. So like when we're doing training, it's like kind of like we're doing back propagation, like since the gradient would be at 0 there, then what happens is it's not going to really train. So it's like, it's basically a dead neuron. I think that's the term. Or yeah, the gradient just zeroes out. So then it's like kind of stuck there, so to speak. So that's why I added some batch normalization layers, and then got some training. Loss kept going down. But then I realized I made a mistake. Like I was debugging both in a VS Code and in a I was also debugging in VS Code, and I was debugging like in the browser itself. And I noticed that there was a bug. Once you notice a bug, I have to kind of revert like I had to revert like this stuff. Wait, did I not revert that? Huh. Anyways, the main thing I did was I fixed the GameState.clone not properly cloning all coin fields, untested but obvious. And whenever I have to like change such a thing like this, when I fix the GameState.clone, like that's the thing. Like if everything is bug free, then you just run Alpha Zero. You wait a week, a year, a millennium, whatever, and then hopefully like it works. I don't know, but like if there are bugs in the code, then like you're gonna get garbage results, right? So like once you kind of like do a fix, you have to kind of reinitialize the neural net, right? And then I did some training and some training, and then the sad part, I was kind of hitting some issue of like I was hitting an issue, I guess, like saturation or something. Like the tan H value output head was always returning like 1 or -1 or something. And I was kind of stuck there. So I kind of like, I added like one more dense layer. I did some more batch normalizations, and I just kind of redid everything. Okay, you know what I'm going to do? I'm just going to do a git diff. So like, I did a bunch of changes since last stream. So let me just actually like, summarize like everything, and like from the currently where we're at to where we want to be. So git diff whatever. Oh wait, no, let me actually first commit my changes. Git status, git commit. Let's call this latest status. Okay, great. So now let's just kind of do a git diff of the commit we did from last stream, and then let's just do head, right? Which is like where we just are after latest. So okay, here's the key thing which I realized, like it kind of sucks like training for like 3 or 4 days and then like realizing your results are stupid, and then kind of like debugging, like stepping through every single thing. And I noticed that like the healths of the coins, even like when they've hurt, like the healths were always 1, right? Like the healths were never actually decreasing when I was doing training. So like, wait, am I streaming? Wiggle, wiggle, wiggle. Okay, good. The mouse. Okay, so I'm live. Anyway, so like the health was always fixed at 1 to the inputs of neural net. And I realized when we're cloning game state, like for example, like when we're doing MCTS, we call clone to advance to like not destroy information. And then we also call this game state.clone when we're doing symmetries, when we're flipping something about symmetries, also in MCTS and in training. But yeah, so anyway, I noticed that the health was never changed. And I realized that we're actually like not cloning it. Like I kind of copied the clone from, I think, like existing BumperCoin code. And like that didn't have to worry about some of these because like, never mind. The point is that clone was like, I forgot to clone this field, the health field. So like whenever we're calling neural net on some coin, it kind of always assumed that the coin was fully health. So like the battle damage wasn't reflected. Basically there's a bug in the clone, and because of that, the whole MCTS loop, the whole training, everything is basically wrong. So I had to kind of like delete the neural net, rm-rf it, and like recreate the net again. So anyway, so that's like a huge bug, and that's like the only bug I really found so far, I guess. I mean, that's the thing. If I find a bug, that means I have to kind of discard everything and start from scratch. So that's kind of annoying. Then 1000 is too much. I just made it 150. Because it takes too long. So here's the architecture. So now there are a whole bunch of like, okay, let's just kind of go line by line. Like there's 4 conv layers, and now like there's like ReLUs, but then after each activation, I kind of have a batch normalization layer, and then I have oh yeah, and also like one thing I saw was like there's like a debate about like, do you want your batch normalization before the activation or after it. And as for that debate, like, I mean, I've seen people like I'm not really qualified to talk about that, but I just kind of yeah, I just stuck it in between because I wasn't really sure how to do that, to be honest. I mean, never mind. I mean, whatever. I mean, either way, adding this did make the loss function change, so overall it did the job. Anyway, so like, I have a comment. Default data format is NHWC. So like C, like this channel's feature axis is like the last one. And the batch norm always defaults to -1, which means last. It's the same as 3, right? Because like 0, 1, 2, 3, or 0 and then 1, or 0 and then loop around to -1. So yeah. Anyways. Yeah, like in Java, you'd get like some error because like it's just 0 to the length -1 when you're indexing out of bounds or out of range, whatever. But like, and I guess Python or JS, maybe, I'm not sure, like -1 kind of loops around. So the point is that we can just take a batch norm and we don't have to specify the axis because since we're in NHWC format, like see the channels dimension is like if you look at the input shape, number of channels, that is the feature dimension. So the normalization is doing the correct normalization. Like it's doing it over the correct axis, so that's good. Then like the same, only difference is all the 32 filters, I made them 64 filters. I believe in Connect 4 we used 128, so I'm like, you know what, let's just scale up the capacity a bit. So we have more parameters, more filters, and we have a bunch of batch normalizations. And then after flattening it, we have a dense layer. Instead of dense 1, I realized there's no more denses really, so let's just, I mean, there are, the outputs are technically dense, but I just called it just dense. And then here, basically same thing. Wait, what? I guess just dense 1 to dense, no other thing really changed. And then after this dense, I think it's crucial to do another batch norm again after that dense. And then policy output and value output are basically the same thing, except rather than do them on the flat, or I mean, sorry, rather than do them on the dense, we have to do them on the batch norm. So yeah, that's basically it. And everything else is the same. So basically a bunch of batch norms issues. And then we made this from 200 to only 1 because each game takes far too long. And then I also added a console.log statement, number of examples per game, just so that like we know how many moves the game takes, because each move we do like 150 or 151 model.predictions. So like this basically kind of is a proxy for how long it'll take to train. Like, yeah. And then here's of course like since we change the model architecture, like we have to create the new model, and then the weights obviously are different too. Just a binary file. So that's where we are right now. Get status. So yeah, and then let's just actually go back to our, what do you call that? The notes, right? So training is super slow, and then tweak game. So then here's another like kind of like proposal, like tweak. So like tweak the game mechanics. Wait, hold on. Sorry about that. Shoulders hurt. Okay, that's better. Yeah, so it's just being full screen. Tweak game mechanics to have the game finish faster. So increase physics.damage factor constant, so coins do more damage when they hit enemy coins. Cause like yeah, like each turn, like each game, well, I guess this is out of date. Like these things are out of date, in fact, because it takes more moves now. So increase the constant so coins do more damage when they hit enemy coins, or we could add some decay on coins' health. And then not too concerned this result is worse results in worse policies because like basically we're training for a different game variant, but we're already doing approximations like in the variant. So like it's like yeah, we've already made a ton of abstraction, so why not make more? Like my idea was let's just kind of like the games last a very long time when training, and that's a huge like bottleneck in terms of time. So like if we can kind of make the game end faster, then we can get some like more information. Like we can kind of make the whole loop a bit faster because right now the limit seems to be time. I mean, yeah, and then add some decay another way just to like yeah, just have the game finish faster. And then this actually does result in training bots for a different game, but we've already made so many approximations, like what the hell, why not make more? Then shrink the game board size from 15 to 20 to something smaller because like it's kind of like ideal gas law, right? Like PV equals nRT, like we're kind of like particles colliding. If we kind of shrink the game board, the more collisions and like yeah, more coin collisions, so presumably faster games. Also, side like another moreover neural net would be smaller, so the predictions would run faster, less parameters in the network, right? Then we can look into all because like basically I've kind of hit a point where like the training is very slow. I'm not really making much progress. I'm just training one game at a time. And like that's like ideally you want to train like hundreds of thousands of games per iteration and like hundreds of iterations. So like it's a whole like we're orders of magnitude slower, so that's kind of a bit sad. So I'm basically I kind of like I'm like, you know what, like here's where we are. Like this whole note is basically like some reflections on like what's happening, some possible ways to like improve, like some kind of next steps, I guess. So, anyways, alternate M approaches. So here's what I'm thinking, like supervised learning, because like before they did AlphaGo zero, like zero is like zero knowledge or something. Like they had AlphaGo, which kind of actually like trains the like. In fact, well, technically zero involved like one neural net, which is both policy and value outputs. But the original AlphaGo, there were two separate nets, each with like one for policy net and like one for value net, kind of like actor critic, like just the policy in the value, and like those were actually trained like on existing like games. So the initial one, like we want to train the neural net on prior game replays before doing the self play, like before actually like doing the so-called alpha zero like self play learning, where the bot plays itself and like the network plays itself and does Monte Carlo policy improvement. But like rather than doing that, like because like right now it's like kind of like where's the signal, right? Like if the neural net has garbage like weights, then like the coins hit, it'll take a very long time, and like what's the actual signal, right? Like it's when we hit a terminal state, right? Like when the game ends and then the reward function gives like +1 or -1 or technically zero, but that's like very rare. I think maybe even never. I don't know. Like +1 or -1, then like it's kind of like back propagation like from the end, because that's like a definitive signal of like +1 or -1 reward, and as that propagates up, like that that's like kind of nice. But like there's so many like moves that like by the time like we finally like hit those terminal states, like a lot of garbage has happened, right? And like from there we're kind of like going back and forth. Like if you're like almost at the end, then the search like kind of guide you to the winning or the lose, or it would guide the winning player to like the terminal state of them winning. So the policies they learn then are pretty good, right? They're pretty nice. And then hopefully like kind of like makes its way back to the beginning. So like that's kind of like the idea, but it's a very long journey for the signals to propagate from the leaf node, the terminal node, the game over to more earlier opening stage, right? Now again, what I'm saying is kind of my view of how this stuff works. It may not be correct. It's just like my thoughts, I guess. But anyways, but the point is that like since it's so drawn out, like the games are so drawn out, like there's not much progress made until like the end. Like it's just like like garbage in garbage out. So like yeah, like that's why like you want to make some progress, right? Like you want the network to move the coins in a reasonable way so that like stuff's actually happening. And that's why like maybe we can like train it from like existing like players, to kind of make the bots like some baseline level of strength, and then self-play will like kind of skyrocket that. But like you want some starting point, right? Like right now the bot has negative elo, so it's like pathetic. And then, but the only problem with that is we only have like a few hundred, like maybe like 500, 600 game replay files. And like, yeah, I doubt we can really learn much from that. Like in chess database or whatever, AlphaGo or like Go data, like you have like millions of games to like look at. And then there's transfer learning, which is like kind of back to the shrinking game dimensions, like from 15 by 20. Maybe we can train from like something less, a smaller game board, and we could try to reuse those neural net layers. So it's like the same idea of like kind of like reusing these existing layers and like kind of like doing some supervised learning. The whole point is like before we do self-play, like we want to kind of have our nets have like non-garbage parameters so that it's doing something sensible, like something understandable. So like it's a good starting point. It's like these both are kind of like similar concepts. It's like kind of like giving it a bit of a push rather than like saying, hey, you're all on your own and like you'll take forever to like make improvements. I don't know. Then multi-threading, like the main bottleneck is the self-play. Like I talked about it a lot, and look into parallel algorithm. Like there's some like I've seen like lots of people do this parallel stuff, like where they kind of have like dummy wins and dummy losses or something. Never mind, but I don't want to do this because that's too much work, and like again, I have to run it for Connect 4 first. It's like I already have something that works for Connect 4, so it probably works for this too. I I'm not going to say I'm supremely confident in the correctness, but I think overall it's doing the right thing. And then rewrite into Python, because like that's what everyone's doing in machine learning. Like you can use the Jupyter Notebook, many machine learning libraries to choose from, like TensorFlow, like PyTorch. Like there's so many different things to choose from. And then easiest development on external compute platforms like GCP or like some other stuff, like where you can just kind of you can actually like hook up your Jupyter Python like to like connect to their thing. And I mean there's like it's just very easy to do, whereas JS is like I'm using TensorFlow JS and like it's not like ideal. But then it's again, I don't really want to do this. Yeah, I have some code. Never mind. The point is that like I don't want to do this because like it's a lot of work. I have to rewrite the physics engine to like to run Python. It's basically rewriting significant parts of the game in Python, and like that's kind of a huge hassle because like the game's already written in TypeScript. So I kind of want everything to be in JS TypeScript compatible so I can leverage like the existing physics engine for free as opposed to like rewriting it from scratch. So like I mean this is like kind of like if I really want to like this is something that like it might be the best approach long term, but I hope I don't have to do it. So anyways, general plan is to get something working locally before kind of spending money on compute. Like before I convert everything into Python, I run it on GCP or something or Google Colab or whatever. And I did try a bit of that. Anyways, like before doing that, like kind of spending money on like cloud credits or like GPU or whatever, or like buying a graphics card or something, like I want something to happen, like some proof of concept, right? Like I want to see like, only if they're kind of showing some intelligence and understanding, only then would I want to actually like spend money. It's like if you see only if, like it's like if you have only if A then B, that actually kind of flips the if and then logic, which means like if you have like only if A then B, that's like if B then A. It's not if A then B, which means that like if I end up spending money to improve it, then that means that the current bots locally kind of are doing something reasonable. It's not the other way. Like if they're doing something reasonable, that doesn't compel me to spend money. Maybe I could just keep it up and get better bots. That's just something I find kind of interesting and like never mind. The point, okay, so then feel it's a note when you see it rather than, and yeah, right now the bots suck. In fact, after I go through these notes, I'll show a demo of like me playing the bot. And again, sadly, I'm unsure if this is even feasible, so it might just be, yeah, and then anyways, like the rest of the stuff are kind of like useless. So anyways, yeah, I'm saying that like from grass, I've seen from Alpha 0, AlphaGo, like typically like stuff jumps out really early and then slows down as the net kind of saturates. So yeah, that's all. Yeah. So let's actually like, I mean, all that talking, let's actually see how the bot performs, right? Like right now, if I kind of like do a PS here, you'll see that I'm running like 3 servers. Like one is the game server, one is the matchmaking server, and one is the game server, matchmaking server, and the front-end server. Technically, I only need the front-end server for this. The other two are useless. But anyways, yeah, let's actually kind of play the bot, right? Oh, sorry. Let's kind of play the bot. Boom. Here's the bot. Okay, it's making a move. It's making a move. It's making a move. Okay, I'll just quickly finish it off. It's moving the king. It's kind of bong clouding because it's stupid. All right, let me just, oh, okay. Oops, I missed. I mean, it's only moving its king coin. The other coins, it's like playing with only one coin. Okay, it's finally moving something else. But like, it's not like, it's just like being passive and like kind of ridiculous. It's not really like, okay, it's not really showing any sign of like life or intellect. It's just kind of being super sluggish. So yeah, in fact, like, and I have some breakpoints set, like, let's just kind of open them up, or one breakpoint set, like right here. And so get policy and value, basically, like, I have a breakpoint in this function, get policy and value. And the reason I have that breakpoint is to kind of like see the current state of affairs, right? Is to currently like see what the net is thinking. So like right now, if you look at like the value, it's saying negative 0.999. So that means -1. So like whoever's turn it is, like the game state, who's the P1 turn? So right now, like if you look at the game state, P1 turn false means it's the bot, is negative 0.999, right? So that means that like the neural net right now, given this game state, well, it could be a symmetric version of this game state too. It doesn't have to be this game state. Technically, it thinks that the bot is losing, right? And let's just kind of see some more predictions. And right now, if you look at this is 0.999, so it's like almost 1. It's saying is P1 turn is true. That means the human is almost winning, which is looks reasonably correct. Now, in fact, again, like when I say like this could be symmetric, let's actually see if we have a symmetry. Let's kind of like look at this and the way I got this to work actually, because I remember lamenting that service, like the service worker, this web workers like JS wasn't really like showing stuff. I had to like go to some settings and like I had to do some like thing to see everything. But anyways, it's better than actually going here and like manually expanding everything out each time. I can just see it here. Something called line wrapping or something got it to work. Like settings. Never mind. Oops, sorry about that. But how to get it to work? Oh yeah, I basically like selected wrap lines, and then because of that, like I can see everything nicer. But anyways, actually, yeah, let's just actually like have a look at this game state to see if you have a symmetry, right? So game state, print coins discretized, boom. You see that right there? We can see a flip, right? Like you see this one coin kind of down here and to the right, and then everything, like if you kind of like pretend that this line right here is like the equator, then there's lots of stuff in the northern hemisphere and only one stuff in the southern, which is super right? But now if you look at here, like we have like the same thing, like this is like the equator. We have like 1, 2, 3, 4, 5 coins like in the northern hemisphere and like one in the south, right? But so it's like we've flipped horizontally because like it's like this coin here, like if you have like dot like kind of like we have like this, right? And then like, if you look at the southern one, like one is an extreme right in the actual game state, then like in the game state we're calling the net on. Notice that like this one in the super right actually becomes in the very left. You see that? So basically what's happened is the same connect for symmetry. We've actually flipped it. We're not calling the neural net on this current game state that we have here. We're actually calling it on the flipped version of it. You can see this coin here it ends up like from going super right to super left. Now, if you look at these two coins, they're probably like these two, but like you see how this angle is kind of like, it's not like a straight line. These coins are not on top of each other. There's kind of like a backslash dynamic going, but when you flip it about the vertical axis, it becomes a forward slash. You see that? Like you can see the contour, like it's kind of like a forward slash, whereas a backslash. So we can see that the symmetry is doing the correct job. In fact, we can actually look like this is 1, right? Like every single coin here has some damage, except for one coin that's so amazing that has taken 0 damage, right? And that coin is my coin, my king coin. You see how like this coin in the actual game is like a little bit to the left. It's more on the west than the east. Whereas now here, this coin is actually, if you look at all the coins, this coin is most to the east. It's most to the right. Because when you flip it, then what's most left becomes most right. So we can see that like the state, like the game state here, whereas the game state that's currently being like kind of debugged upon, we're calling get policy and value. The main difference is like the symmetry is that it's being flipped horizontally. So yeah, the symmetries are working as expected. That's good. And again, like I said that like this coin here that's like proudly standing unaffected, like triumphantly, like just like not backing down, just one. Like that coin I said is my coin and I am player one. We can actually verify that, right? Game state. Actually, well, we can actually like expand it out. Like if you kind of look here, right? Let's kind of look at this game state and let's like the game state. The coins, yeah, is player one or whatever. Like player one's turn is true, and for player one, it's thinking that's about to win. We look at the coins, and then we kind of look at my coin. That's the king coin, player one. Look at the health. Boom, 65536. Now that means full health. Why? Because that means full health. Like look at the other ones, they'll be less, right? Like this one's health is a 6-2, and then like this one is a. Sorry, this is my king coin, full health. This is my full health. And then this coin for 2 is, its health is, sorry, it keeps going back there. It's less than that. And then, like, this one is less than that. And then this one is, its health is, I hate the scroll bar, is very bad. In fact, this is so bad because, this is the king coin for the bot, is player P1. Because I'm P1, bot is P1 false, player 2. Or not P1, right? And the last coin again is its health is 50 in the 50s, right? So like my coin, my king has 65536, right? Again, why does this mean full health? Because if you look at like 1 or 2 to the power of 16, that's 65536, right? So that minus 1, right? Or that one, right? That's just the fixed point conversion, right? Like if you look at my fixed point library, GitHub, fixed point JS. Again, like if you look at like the it's a 16.6 or 15.6. The fractional part is a 16. Like, yeah, the scaling factor is like 2 to the power of 16, or it's reciprocal, because 1 shifted left shift 16. So yeah, that's just kind of how it works. That means it's full health. So anyways, so we can kind of see that like the net, like the valuations it's doing is like, I mean, it can see who's winning, something not. Now, one thing I noticed is like if you look at like the like what it's returning, like I was facing an issue of like saturation for a 10H, like the value output, where like one thing I noticed was it was only like returning like 1 and -1 or almost 1 -1 very often. Like you see it's like almost 1. Like player 1 is almost, let's forget the players, but like let's look at this thing, the magnitude. It's like +1 or -1. Magnitude's like 1. 1. Okay, 0.25 finally. So this thinks that the bot is actually slightly better by 0.2. I mean, that's a wrong prediction. That's fine. And here it's saying the bot is losing -1. But overall, let's just ignore that. Let's just only look at the, let's just like, see it's like -0.99. It's giving very extreme. It's like a binary decision, between -1 and 1, right? Like there's not so many like 0.2, we only saw 1. Like, hey, like player 1 is really winning, or like player 1 is almost winning. But in general, like there was once a time in training after the first few iterations where I only saw 1 or -1. And the reason why that's happening is like kind of like similar to ReLU like being a dead neuron. Like what's happening is like if you look at the actual like kind of like 10H function, like the 10H activation function with asymptotes of -1 and 1, it's like something like It's like something like this and like this and like this, right? Where like this is like kind of like the origin. That's the origin. So like the gradient, like if it's too negative or too positive, the gradient's like almost zero. Like it's a bit angled. Like there is some gradient to it. Like there is some gradient, but it's super tiny. So when we're doing training, like that's almost zero. So like it's kind of like similar thing with ReLUs, where like if you're kind of at the negative point, the gradient's zero. So like the weights won't really change that much during training, assuming that like the activity, like the input to the neuron, like is a negative or whatever, or is like here the magnitude's greater than one. That's why the Batch normalization helps. But there is some gradient to work with. So in theory, hopefully, like with training, at like first, I had a problem where it seemed like 10H was saturated and always returned like one or only return negative one. It didn't really change much. But as we can see now, like there's some like 0.89, like that's not magnitude of one. So like as I keep going, it is like the values are making some sense. Like player one is doing relatively well. Again, plus one from the perspective of P1 turn true or not. Like plus one means like they won or they're really winning. Negative one means they're really losing, and zero means a draw. And we haven't really seen much zeros. We've only seen like something extreme. I guess that's kind of reasonable because right now if you look at it, like their health's super low and mine is super high, and like I'm pretty safe. My king and their coins are pretty useless. So like I mean like the net seems to like the valuation seems to show like some form of like reasonableness, but like overall it's a pretty weak bot. Like I won with pretty much no effort really. And like my king like was undefeated. It wasn't even scratched. Like it wasn't even like hurt a single bit. So like yeah, this bot doesn't show any aggression. Like if I click rematch and do nothing, the bot really like makes like it doesn't really kind of go after my king. Like it just kind of like sometimes I notice just kind of like loops back and forth and like basically like does nothing at all and like it's an infinite loop. So like as you can see here, the bot's not really like showing any signs of advancement. And that's kind of why I was hoping that like I was hoping that supervised learning, like if it learns some initial policies, like by imitation learning or like yeah, then like if I train it on a bunch of replays, maybe it would learn early on how to play the opening, how to actually bring the king coins towards my king. Like right now, the moves aren't really achieving much, right? So yeah, it's kind of a really shitty bot, but that's where we're at, and that's yeah that's just where we're at. So I mean, it like each turn like training it takes such a long time. Like each like currently the last time I trained the bot took 2.8k seconds. Like let's just take that, right? Let's just copy that and like let's just actually convert that, right? Let's just see how long that lasts. Divide by 60 because that's always that's seconds or milliseconds. Sorry. Yeah. The that is seconds. So dividing by 60 goes minutes, right? Yeah, 46 minutes. Like playing a single game, which you wanted hundreds of thousands of, millions maybe, but a single one of them takes like a good chunk of an hour, like 3/4 of an hour. So like it's really not, it doesn't seem to be feasible to like execute this alpha zero. So that's kind of a bit like that's just the way it is, maybe. Like I'm not sure like how many rounds I have to train to like get something that's good. Like it seems that like I may have to do some like tweaks that I talked about, like some supervised learning, some I was thinking maybe like increased damage factor, like kind of parallelism, rewrite in Python, and like I seem to like yeah, the training's super slow and like not much progress really seems to be made. So like I don't know. I don't know. Um but yeah, like overall like the title of the stream's like training update question mark, and like that's just yeah, that's just where I'm at right now. And like here's some like brainstorming, some possible next steps, some stuff I'll do later, but like some avenues to explore, but right now here's just what I have. So I'm guessing what I'll do probably is just publish this live and like I don't know, like here's just a I mean, I've done everything. So I mean, yeah, here's where I'm at and like here's next things to do. So I'll see where that goes. Maybe I can try some more stuff, but for now it seems to be generally a failure. So that's kind of a bit sad, but But yeah, I mean, yeah, that's just where we're at right now. So I'll just end. I just gave an update of training, and I think I'll actually deploy this live. Like right now, if you like look at the like 127, like if you look at this, like you see there's three buttons like play private maps. I'll just add another button like saying like experimental, like beta or like in progress, or yeah, experimental colon like alpha zero bot or something with like some like page like here where maybe you can click and there'll be some info page like maybe the number of iterations of self plates learned, like some kind of status or something, like just some way for players to like play against the alpha zero bot. And like in theory, I'll mention that like every week or something, or I'll update the bot to make it hopefully a bit stronger, like after some rounds of self play or whatever. So yeah, that's basically it. Um, yeah, basically training seems to be super slow, and that's it's not. I'm not really getting to see much progress because of the how slow it all is. So yeah, that's all.